So again, all hands, all lands. There might be a talk that will come later that might help you understand with that fuel component, we'll see. Or it will be a future topic for discussion. So hold that thought. Moving on, continuing on the climate change sort of theme here this morning, Crystal Raymond is with the University of Washington. She's going to talk about forest fires in the Western Cascadia, evaluating climatic drivers to inform climate adaptive management responses. So help me welcome Crystal, everyone.
Great. Thank you. I'm Crystal Raymond with the Climate Impacts Group, and I want to acknowledge some co-authors on this, and this research has been a great collaborative effort with Nick Bond and Karen Bambacco from the Office of the Washington State Climatologist, Josh Holofsky and Dan Donato from Washington Department of Natural Resources, and Brian Harvey from CEFS at UW. So this research came out of a workshop that was held in 2018, focused on West Side Fire. This was sponsored by the Northwest Climate Adaptation Science Center and the Climate Impacts Group with the Tulalip tribes. And we wanted to get a group of people together to focus on West Side Fire, so pretty similar to this symposium. This was back in 2018. And I think we had really could have had no idea of how much this topic would have grown in the interest that people would have in this topic in just 5 years. In part driven by the Labor Day fires, but also just an increasing interest in understanding how to take this information about wildfire in this region and climate change and what to do about this, both in terms of thinking about the ecological implications, managing forests, but also in the wildland-urban interface in terms of protecting communities and emergency response. So in this 2018 workshop, and I encourage you to check out this summary paper of the workshop, we really brought people together from really different backgrounds: emergency response, land use planning, ecological management of landscapes, to say what are some of the key research questions and information needs that needed to be addressed on West Side Fire. And for this project, some particular partners that we've worked with are the Tulalip tribe, the Mount Baker Snoqualmie National Forest, the North Cascades National Park, and the Puget Sound Climate Preparedness Collaborative, which is kind of a group that represents some of those wildland-urban interface land use planning and emergency response aspects of the question. And so I'm going to focus on two aspects of this question that came out of this research agenda, particularly focused on the climate-fire relationships. So we were asking the question, what have been the real climate or weather drivers of West Side Fire historically? And that was something that we wanted to pursue for this research, to really say, could we pinpoint what are the key variables that really drive fire in this region? And then looking ahead, how do we expect that to change with climate change? And so in this case, looking at some regional climate model simulations that we hope would better capture some of the variability in climate in this region in particular. So I'm going to talk about two different statistical approaches that we've used to look at climate-fire relationships in this region. And so this research is a little bit of a kind of a statistical analog to what you just heard from Alex. So what we want to do is first figure out, what are those key drivers of fire in this region? What are the particular weather variables that are most important that we can pull out? And so we did this in two different statistical approaches, and I'll go into just a little bit of detail about these statistical approaches. But generally, I want to make the point that we looked at these two different approaches in order to see if we get similar results. So kind of tackling the problem in a few different ways. Do we come up with the same variables that matter in the same sorts of relationships? And so the two approaches we used were general additive models. The response variable that we were looking at is acreage burned on the west side, and looking at a number of different environmental variables in each model. And then we used a random forest approach with 100 regression type decision trees. And what we see is that using these very different statistical approaches, we did come up with very similar relationships and thresholds for the critical environmental variables. So to say what sort of fires we were looking at for this, so we had about 27 fires. So one of the common problems in looking at climate-fire relationships in this region in particular is the lack of data. So there are many papers that have looked at climate-fire relationships across the West, and typically this particular region for Western Cascadia, we're talking about kind of this region in western Washington, northwestern Oregon. We really have a limited set of fires in the contemporary record in order to do this sort of analysis. And often we find that this region gets lumped into bigger regions in the West in order to get at fire-climate relationships. And really the goal here was to drill down specifically on the variables that matter for this particular region. But given the limited set of contemporary fires, that can be pretty challenging to do. But we used about 27 fires, 1,000 acres or larger, from this area, focusing just on that west side component of the fires. And we also wanted to really look at what is the key weather and climate drivers for particularly when the area burns in those fires. So we also narrowed it down a little bit more to look specifically at the days when the most area is burned in those fires. And so one of the ways that we did this was to use some MODIS fire progression maps. So as a lot of you are probably aware, that one of the challenges we have in understanding the fire-climate relationships on the west side is that often these fires can get ignited very early in the season, June, July, and then often west side fires will just kind of sit in place and not really take off. And then it can be, you know, several months towards the end of the fire season where you really start to get temperature, wind, or dryness conditions that enable these fires to take off. And so we really wanted to drill down on that particular day when a large amount of the fire burned. So we used the MODIS progression maps for each of our 27 fires to basically identify the day of the greatest amount of area burned. And we used that as the response variable. And then we kind of threw the kitchen sink at it in terms of looking at all of the different sort of weather and climate variables that would be, could be particularly important for understanding how much area burned in those fires. So we grouped these in 4 different areas. So we looked at a number of different variables related to precipitation, knowing sort of short-term, long-term precipitation through the season could be important. Looking at wind, so a number of recent papers have really emphasized the importance of wind, and particularly east winds in fire on the west side. So we had a few variables related to that, wind speed, the east wind component. We looked at temperature itself, short-term, long-term lags of temperature. And then we also looked at a number of variables that we kind of lumped together and called thermodynamic variables, which were sort of the combinations of temperature, precipitation, dryness, so things like ERC, vapor pressure deficit, and EDI, the evaporative demand drought index, and kind of said, went through a sort of a systematic approach of looking at these variables individually to say how much did they explain that pattern of area burn that we were seeing in the west side. The majority of the variables came from GridMet. We did find for wind that the better source of wind data that we use for this is actually a regional climate model simulation, the WRF model, developed by PNNL that simulates about 1980 to 2020, kind of the historical climate over that period using the WRF regional weather model. And that's where we got the wind speed and east wind component. And so what we found, kind of the take home from the general additive models, so these are basically regression models that allow for nonlinear relationships among the variables. And we found that wind speed, in fact, just wind speed itself and not necessarily the east wind component, and a couple of different aspects of temperature turned out to be the variables that explained the most variation in area burned. And so we evaluated these models in terms of the variance explained, so how much of that variability in area burned, as well as AIC, which basically meant, kind of penalizes if the model is too complex. So going with fairly simple models here that explain a lot of the variability in that area burned. And so wind speed, not surprisingly, turned out to be the variable that explained most of the variation in area burn. So that's one thing that we've heard a lot about in the last few years from the literature, is how critical wind is to wildfires in this region. But it wasn't only wind. We also found that adding several other variables did explain more of the variability in area burned. And so the two that kind of stood out on top were the 7-day maximum temperature, so 7 days prior to that day with the most area burned, and the 60-day maximum temperature. So despite looking at some more integrative variables related to fuel moisture, fuel dryness, like ERC, we actually found that temperature turned out to be kind of the simplest and one of the best predictors. And a lot of these models were quite similar in terms of how much variance explained, but temperature actually turns out to be a pretty convenient and useful variable in terms of looking at thresholds moving forward. And so this is without interaction, and so basically what this plot shows, this is a contour heat map plot showing wind speed and maximum temperature, and the steeper the lines, the stronger the relationship. Increasing wind speed, more area burned, increasing temperature, the 7-day maximum temperature, more area burned, and we really see this kind of in this upper end of this plot where you get tighter lines and see with these variables increasing a much greater amount of area burned. Oops, uh-oh, I might have hit the key you're really not supposed to hit. All right, okay, with interaction, so looking at those models without allowing those two variables to interact, so I don't want to get too much into the details, but I do want to say we did then allow these variables to interact. So basically, in short, what that means is looking at the combination of temperature and wind speed in the model. We found that when these variables do interact, you explain much more of the variability in area burned. And so you can see that differently in this plot, particularly in this area. When you're at higher wind speeds, temperature explains much more of the variability. So when you're at low wind speeds, actually temperature didn't explain that much of the variability in area burned, but once you get to higher wind speeds, then the difference within the area burned actually then does relate to temperature, and when you have higher temperatures, then that was associated with more area burned. So the interaction of these two variables actually explained about 85% of the area burned from that record. So fairly good models. Okay, and so what we wanted to do was then say, if we could pull out the particular environmental variables that matter most for understanding area burned, then and determine thresholds associated with those, then moving forward, looking at the regional climate model simulations, we could say, how does the likelihood of crossing those thresholds change in the future with climate change? And so from these models, we pulled out these particular thresholds. The first set of thresholds being when you really start to see fires happening on the west side. So including our smaller fires, 1,000 acres, 10,000 acres, 20,000 acres, we really don't see fires unless we get over these particular wind thresholds. So about 9 miles per hour, 7-day maximum temperature of 18 degrees, and 60-day maximum temperature of 17 degrees. So that's when you really start to get fire. And then we had this second threshold to say, when does area burn really ramp up on the west side? What thresholds matter there? And this is really those big fires like the Labor Day fires. What sort of thresholds are we crossing when we see those very large fires? And that threshold is about 25 mile per hour winds and 24 degrees C for both the 7-day and 60-day temperature. So these thresholds then allow us to kind of query the regional climate model simulations and say, okay, how often do you cross those thresholds in the future? And particularly what we want to look at is the combination. So when do you get both the temperature and the winds that give you that climate setup for having wildfire on the west side? This is just one other plot to mention the random forest technique. So what I want to say here, mostly in emphasizing these, is this shows the strength of the relationship. And again, we saw very similar thresholds. So, sorry, these are in meters per second, but here is kind of this particular threshold where you really see this relationship ramp up with area burned. So this is equivalent to that 9 miles per hour, but about around the 25 miles per hour. So that's where you really see a pretty dramatic increase in area burned. So about 25 miles per hour, or 11 meters per second in the wind speed. And similarly for the temperature, here's where we see that 24-degree relationship where you really see these big fires in the area burned ramp up. So the point of showing these plots is to say that, again, this very different statistical approach yield very similar thresholds and relationships. Okay, and then I'll just finish up by talking a little bit about where we're at with the future projections and how we're looking at whether or not we'd expect to see crossing these thresholds change in the future. And so we used 12 regional climate model simulations. So this is the WRF model driven by the global circulation models. And from those, not surprisingly, of course, you see the number of days above 24 degrees C, that threshold. The 7-day and 16-day maximum temperatures, you see those increase, not surprisingly, right? Getting warmer. Many more days per year where you cross that threshold. And we see that, throughout the region, there's a little bit of spatial variability, but quite a few number of days where that particular temperature criteria is crossed. Wind turned out to be a little bit more complicated, and so what we've had to do is kind of dig into a different approach to look at crossing of this wind threshold to see how much that changes in the regional climate models. And so basically we found that these regional climate models, which we anticipated would be better at capturing things like winds in this region because of the finer scale of the models. In this case, we actually found that there's a lack of windiness in general in the regional climate model, so a pretty negative bias in the wind in these models. And so when we're trying to look at crossing a particular threshold, like the 9 miles per hour or the 25 miles per hour, we're not able to do that because in general, the winds are much less than would be expected in the regional climate models. And so what we're doing now is kind of taking a different approach to get at this wind and crossing that wind threshold potential in the future. And so what we've been working on with Nick and Karen from the Office of Washington State Climatologists is really digging into the sea level pressure patterns that result in that windiness. So recognizing that typically when we get those really windy days, something like 25 miles per hour or more in this region, we usually have a pretty big difference in the sea level pressure. And so we have selected Eugene and OMAC to kind of the difference in the sea level pressure across this region. So that's the kind of setup that tends to result in these really windy days like we saw in the Labor Day fires and creates those kind of regional high windy days. So using this now as a kind of more reliable indicator to get at how much more frequently we'd expect to see those high wind days so that we can look at that in combination with the temperature. And so to show kind of what this looks like in the historical record, so this is looking at that pressure difference between OMAC and Eugene, a positive pressure difference generally resulting in these windier days, and two particular thresholds that stand out here. So when we cross 200, difference in the sea level pressure, or 800 being these extremely windy days, east winds throughout the region. For example, here is where that delta of over 800 for the Labor Day fires. And so we're taking this as an indicator. It's something that we're hoping is more easy to pull out from the regional climate model simulations. And then we can look at the frequency of crossing this threshold moving forward rather than the wind speeds themselves. So with that, I'll just conclude. So key messages that I want to leave you with. So wind in our analysis did stand out as a major driver of area burned in the west side, but it wasn't the only one. And looking at a host of other environmental variables, temperature, the 7-day and 60-day maximum temperature stood out as explaining additional variance in the area burned. Regional climate models obviously suggest an increase in the number of days that we cross those temperature thresholds. But it turns out that wind is a lot more challenging to assess from these regional climate models. But this sea level pressure difference across the region is proving to be a good indicator of getting at the potential of crossing those wind thresholds in the future. So with that, I can take any questions. Okay, so if I can repeat the question. So I think the question is sort of recognizing that there's a few large fires in the small sample set, and are there other ways besides sort of the influence of those fires on understanding the potential for large fire spread?
Do all the large fires look like the 2021 Labor Day fires, or do they look different from each other?
Yeah. So most of the large fires are those Labor Day fires, given the record that we have. We do see variation so there is some variation within those that is included in the model. And so it turns out there are other factors that can result in the large fire spread. I mean, I think what we see, I think we spend some time thinking about breaking this up into kind of small fires and large fires. And so I think what we see is, you know, generally to get those really big ones, right, you need to have the wind event, but there's still variation within that. And then in order, you do still have a lot of these smaller fires, you know, 1,000, 10,000, 20,000 acres, that happen without the windiness, right? We do get these smaller fires, and those fires can be consequential. Those fires do have, you know, impacts on communities, impacts for response. And so, you know, we do see that there is, that there's a relationship with temperature there that explains some of the variation in those fires as well. So I'm not sure if that's answering your question. I mean, I generally, you know, you don't see these really large fires without having the major wind speeds, but it doesn't explain all of it either. You know, you do see fires when the winds were there and they didn't get large. And so it just says that that some of these other environmental factors do play into the amount of area burn that you're actually getting. All right, take another question. Yeah, that's a great question. And so in terms of looking at the frequency of crossing these thresholds in the future, we have played around with looking at, you know, the entire year, looking at just the fire season, June through September, or, you know, looking May through October, recognizing that potential expansion of the fire season. I think we're still kind of, I think we'll look at it both ways, right? So we want to know, you know, particularly in the fire season, how much more frequently do we see these thresholds cross, but also looking further out, you know, recognizing that as temperature warms, right, you can cross those higher temperature thresholds much more in the shoulder of the fire season, and then say, okay, do you see the setup for these wind patterns also happening at that time? So I think we want to look at it both ways in order to see, you know, whether there is the potential for the expansion of that fire season. All right, thank you.
Thank you, Crystal. So we're going to take a 20-minute break, come back at 10:30. We'll continue to layer on this complexity of these landscapes that were already complex just because of what they are versus the complex history, and now we're talking about the complex future, and I don't know about you, but there's just an awful lot of complexity and unpredictability, so it's time to take a coffee break. If you could be back at 10:30, and remember, I'm challenging you to have some dialogue, try to find ways to take these facts and figures and make them useful to you. So see you back here at 10:30.